Yesterday we learned about the electronegativity scale. And what does the electronegativity scale measure? Okay, specific. What is it measuring? Raise your hand. The desire for an electron. So write that down. It's measuring the desire for an electron. So you know, if you're going to look at it another way, you're really measuring the attractivity of the attractiveness, but attractiveness. I just made up a new word, attractivity. So it's kind of like the attractiveness. So you can develop a test for that desire or attractiveness, its ability to, the desire for an electron, or its ability to attract an electron. So once again, that can experimentally be determined, and it has, how attractive something is. You can look at a magnet, and you can determine attractivity. How attractive, force of attraction. Yes, a magnet can determine the force of attraction. Now from yesterday, we want to predict up here with some bell work the bond type that will form between the following pair of atoms and identify each molecule as polar or nonpolar. Remember, this is important because like dissolves like. Polar things like water will dissolve alcohol because it's like. Those two are. Yeah, show the work though, because people might not understand where you're getting. So sulfur is 2.5, hydrogen is 2.2. So you get 0.3. And in the book states that's going to be covalent. 5 minus 2.5 minus 2.2. Very good. So covalent again, mostly covalent. And last one, strongest nonmetal on top. Otherwise you get, you know, negative numbers, and that's not good.
I need a calculator. I cannot subtract nines.
Well, just make it 10 and add 1.
Wait, what?
1.4. 1.4.
As you can see.
All right, so very good. Right, if you subtract 10, that would be, or 1 would be 1.5, and add 1 is 0.6, obviously. So what is 1.6 on the scale in the book? What does that say in the book?
What page?
It was in chapter 7, I believe, yes. 1.6 is going to be touching close to the covalent, the ionic. See how it's very close to ionic? Now it says it's at the tip of the polar covalent, but sodium is a metal, so it's going to fall into the ionic group. When we look at the naming, and the naming is classifying sodium sulfide as an ionic compound, the bond is what we're looking at here. The bond type is going to be polar covalent because you have to abide by the rules. And the rules, or the table, says 1.6. So it's falling into that 1.6 table. So you always measure twice, cut once, obey the rules. So it is falling between that 0.4 and 1.7. So it is polar covalent. That is the bond type. The bond type that's not telling you that it's a polar covalent substance. It's just telling you what bond type it is behaving like. So this kind of gets there's a little bit of, I guess you would say, overlap, which can create some confusion because sodium sulfide is not a polar compound. Or just correction, is not a covalent compound. You've got a metal right here. Sodium is. They're just asking about the bond type. What is it most similar to? And they're saying it is most similar to a polar covalent substance. Now it's at the tip, remember, because 1.7 is mostly ionic, so it's 1.6. So it's kind of like borderline there a little bit. So we look in the book, 0.5 is what? Yeah, it says mostly covalent, but it's going to fall in between the polar. So it's 0.4 to 1.7 is going to be polar, so it's going to be polar. Because it's above 0.4, right? Now, we don't have to memorize that. We're just using the table. Okay, so this one ends up being 0, so what's it going to be? What's it fall into? Non-polar covalent. Can you write that up there, Kayla? In the book, they're talking about, this is a question that comes from the book. It says, identify each molecule as polar or non-polar. So the first thing you want to do is you want to find out what the bonds are. So that's what we did. We got our chlorine minus sulfur, polar, sulfur minus carbon, non-polar, and then our fluorine minus carbon, polar. That's important because it's going to help you determine what the actual molecule looks like. So over here then we draw it. So we have our sulfur Lewis dot structure, we have our sulfur and our chlorine, and you can see that it has kind of a bent nature to it. Now we could go back and look at the actual Vesper geometry, but you're going to see that the lone pair on the outside, and that's going to push the electrons to the chlorine. The chlorine wants them. You can see right here this is a polar bond. So the chlorine is desiring them. Everybody see that? Electronegativity is the measure of desire, and chlorine, fluorine, they have the highest. So the electrons are going to go in that direction. They want them. Now the next one, B, they show us the carbon sulfide. So here, we've got carbon in the middle. Remember, the goal is to get 8. Both of them have them now, so it's going to be a double bond right here and a double bond here. Does everybody see that? So if we look at the bond between the two is non-polar, 0. So what's happening, this is like a share, 100% share. They're sharing back and forth. There's going to be no area of positive or negative. It's just a complete share because it's 0. So this is going to be an overall non-polar because there's no set area of positive or negative. When you look at polarity, the question is, it's like a magnet. Polarity looks like a magnet. So if you just want to remember that, then you'll understand this and you don't have to come back to it. So polarity looks like a magnet. Polar is similar to a magnet. So overall, if it looks like there's an area of positive and negative, obviously the chlorine is going to be the negative because it has that strong desire, then it's going to be like the magnet. And then our last one here is the carbon tetrafluoride, where we do our bonds, right? Fluorine is a 4, carbon is 2.5, we get 1.5, so that's going to be polar. Does everybody see that? Yep. So we go over here and we're going to draw our polar bonds. So the electrons are going to be pushed out. Fluorine is going to be, I guess you'd say, owning them more. It's still probably a share, but fluorine is going to have more of the electric charge. And that's why there's going to be a negative, because it is polar. This bond is polar. Does everybody see that? If there were one of them, if it was just CF, then it would be a polar molecule. But it's not in this situation. It is CF4. So you have a polar here, you have a polar here, you have a polar here, and you have a polar there. Anywhere you cut this, you're going to have a negative and a negative. Does everybody understand that? So if I have like a positive here and I got negative all the way around it, anywhere I cut that, there's going to be negative here and negative here. If I cut it here, there's going to be negative here and negative here. And that's the definition of non-polar. So overall, it's non-polar. Negative on the outside or no opposite charge at poles. So if there's no opposite charge at the poles, see how these charges are the same? If there's no opposite at these poles, then it's going to be non-polar. Raise your hand and tell me, what does this 2 represent? Hannah?
Subscript.
That's a subscript. And what does this 2 represent? Garrett? Coefficient. Right?
Yeah, the coefficient.
All right, now what does the coefficient tell you?
How many of that was bond or the element that's going to be there, or like what's it called?
Substance. Element or substance, right? So if you have 2 H2Os, how many waters do you have? 2. So it's pretty simple. Coefficient tells you the number that you. It's on the left side of the equation. Raise your hand. Raise your hand. Let's go with Cody.
Reactive.
Cody.
No, I couldn't hear it because you sort of called it like what? I said reactive.
Yeah, the reactants there. Does everybody see that? The reactants. And what does the arrow represent?
The yield.
Yield. Now that's another important key term there, because you'll see oftentimes things above the arrow. Like, have you ever heard of like a catalyst? Catalysts typically go above the arrow. So what do catalysts do? Raise your hand.
Give room for the things to work.
Close.
Helps it happen, like to carry it.
Yeah.
Carry it.
Makes it go faster. Do catalysts get used up in a reaction?
Yes.
No. So you just add a catalyst, it doesn't get used up, it can be used again. Like enzymes that are made in your body that catalyze reactions do not get used up. They just get keep using over and over again until they get damaged, then you make more of them.
Like slash like a disease.
Right, so heat
Like
can
a
be a
mutagen?
catalyst, right?
Like a mutagen. or
Okay.
something?
Yeah, it's true. Heat can be a catalyst. Heat would not be used up, it just allows it to go faster. Heat is probably the most common catalyst that you're aware of. If I heat you up, you're gonna like want to move faster.
Do I?
Yeah, you're like move around the top.
Sometimes I want to sleep though.
Okay. And the brackets represent. What does the S in the brackets represent?
Yes.
Yeah.
Of the state.
Yeah, like what is that? What state is that? Okay, close.
Kind
Is it a liquid?
Yes.
No, it's a solid. Right, so S stands for
For
solid.
liquid.
Solid.
No.
Now, what would G stand for?
Gas.
Yes. What's AQ stand for?
Aquatic.
Aquatic.
It says right there in the arrow there, it
In a
says,
water solution.
so you take salt, right, and you put it in water. That's what aqueous means. Is everybody clear?
Aqueous.
All right,
aquatic.
so, and then what, after the arrow, do you see there? What are those called?
Uh-huh.
Yeah, they're called products. So you typically try to make products. Now in chemistry, we go backwards. Typically we take our product and we break it down. We try to figure out how to make it.
Yeah.
So you find something that works and you're like, okay, how can we make this so that we can sell it at a cheaper price? You ever seen Shark Tank?
Yep.
Yeah, that's generally the idea. How can you make it at a cheaper price? So let's take a look here, some of these equations. How is a chemical reaction going to change the way you drive? Anybody?
An explosion in your car. It helps you move in your car.
Now, are chemical reactions
Like oil.
currently involved in our automobile, Jake? Are chemical reactions currently involved in our automobile? What type? Okay, is that single replacement, double replacement, decomposition, combustion? Yeah, it's a combustion reaction. So the current automobile is a type of reaction called combustion. All combustion reactions involve what?
Oil and gas.
No, starts with an O.
Octane.
Oxygen, right? Combustion reactions require oxygen. That's a very important thing to know if you're going to be what?
Car maker.
A firefighter.
Okay.
Right, there are a lot of firefighters out there, so combustion reactions involve oxygen. So up here, we're kind of shifting to a different type of reaction where we're dealing with like batteries. And in that typical reaction, you're dealing with either like a single replacement, most likely it's oxidation reduction. And why is it going to be oxidation reduction? Why are fuel cells oxidation reduction reactions? That's kind of like the seventh type of reaction, oxidation reduction.
It's taking the oxygen from the air and pulling it up.
Well, you're making a compound from an element. So when you charge your battery, you've heard of the Tesla, right? It's got a supercharge.
Yeah.
Well, when they charge the battery, they're making the metal again. So lithium is the primary metal inside the Tesla
So this
car.
dude figured out how to make metal.
Right, so in order for the battery to work, you have to have lithium. Well, when the lithium gets used up, when it makes like lithium, I'm not sure what the product is, but it's going to be a compound. So when that compound is made, the battery doesn't work anymore. The battery's dead. And in order to get the battery charged again, you have to make it back into a metal.
So does the electricity like separate the lithium from the compound and then just make it recharge like that?
Right, it does that. What you're doing, you're adding electrons back to the metal. So metals have a desire to lose electrons. So that's what makes lithium a really good metal for a battery.
Yeah,
So it can lose them.
Batteries still explode.
Right, you have to be careful because they can get hot and explode.
Batteries are fun.
So be aware of that. So that's what's happening with this type of vehicle. It's still going to be a chemical reaction. It's going to be a chemical reaction because the metal, lithium, is going to be formed into something else. Now they're trying to make lithium sulfide batteries. I don't know what they currently use, but the goal is to make lithium sulfide because it produces a lighter battery. Sulfur is fairly light, if you didn't know that. What's the problem with sulfur?
It's unstable.
It's unstable. It likes to react with a lot of different things. Good job, Gary. 5 minus 2.2 equals what, Rain? 0.3, right? So 0.3 is going to really fall into the mostly covalent, because this is 0, right? So it's going to be mostly covalent. This bond will, mostly covalent.
Is it mostly covalent?
Mostly covalent. Right, if you look in the data table, 266 in the book, it'll tell you that 0.4 to 1.7 is polar covalent, so it is polar covalent. Now sodium sulfide is an ionic compound. And they're talking specifically just about the bond between sodium and sulfur. It is a polar covalent bond type. All right, so once again, write this down on your Avid notes. 2 potassium iodide plus lead 2 nitrate yields lead 2 iodide plus 2 potassium nitrate. So we're just going over the first equation there as an example. Let you do the second on your own.
Plastic and your CDs have something in common. Food fibers and plastic are produced when the atoms in the surface.
Covalent, mostly covalent. So write that there. So that bond type is mostly covalent. Anybody do the next one? Carbon, hydrogen. All right, Kaylee. 2.5, hydrogen's 2.2. Very good. And sulfur is 2.5 and sodium is 0.9.
One point something.
1.6, right? And the book says 0.4 to 1.7 is polar covalent. Now, is sodium sulfide a covalent compound? Gabrielle? Is sodium sulfide a covalent compound? Diana? Brendan, is sodium sulfide a covalent compound?
No.
No, it is what type of compound? It's ionic, because you have a metal and a non-metal. That was the first thing we looked at our naming key. They say, is the metal present? If the metal is present, then it's an ionic compound. So even though this is an ionic compound, the actual bond is mimicking the polar covalent.
So it's still ionic.
It's still ionic. It is an ionic compound. But it's bond. They're asking about the bond. Predict the bond type. It is a polar covalent bond type. That means there's going to be an area positive and an area negative charge shown in this structure. It falls into Lewis dot structures. Sulfur has how many electrons around it? 6. Chlorine has 7, right? So the X's represent the electron dots for chlorine. So we place our chlorines around it because it tells us SCl2. Now, when we just determined the bond type, that is the sulfur-chlorine bond type here, you took 3 for chlorine minus 2.5 to sulfur, and it's telling us it's polar. So that means that the electrons are going to favor the chlorine, just like if you take bleach and you pour it on your clothes. The nonmetals desire the electrons. If you desire an electron, you're going to be negatively charged. Does everybody see how the negative part of this molecule is going to be on the chlorine? Now, Vance just asked, he said, Mr. Sonic, what does polar mean? If this area is negative, right, and this area is positive right here, then you have kind of like a magnet. An area of positive, an area of negative. That's what polar means. Just remember a magnet, polar. This looks like a magnet, so it's polar. Guess what if you're not looking like a magnet, what you going to be? Non-polar, right? Not too difficult. All right, who wants to do the next one? It's going to be non-polar. So the book states on page 266 that if the electronegativity difference is 0, it's non-polar. So up here we see our 0. Don't go away. TT. So you see that's 0? So it's non-polar. Now, we drew over here on the board the the carbon sulfur molecule. So first thing I did was put carbon. How many electrons does carbon have around it? 4. You see them in black? They're the 4. Sulfur has how many? It has 6. So you look in the book and it shows you that. Now the goal once again is to get 8 around all of these. So if you circle here, you'll see there's 8. 2, 4, 6, 8. 2, 4, 6, 8. Carbon has 8 in the center. Now this is a non-polar bond because if you subtract the electronegativity values, it's 0. So that means there's a complete balance happening here. You're not going to see a negative charge in the sulfur. You're not going to see a negative charge in the carbon. They're kind of sharing completely. This is like a complete share. Now you don't see any electrons on top of carbon or on the bottom, so this is going to be a VSEPR geometry of linear. So it's linear, no area of positive or negative, non-polar. Any question on that?
How do you get the electronegativity?
The values are given on the chart. The values are basically about attractiveness. When we talk about desire, we're talking about attractiveness. I can take a magnet and measure its attractiveness. Just like you can take fluorine and chlorine and measure its attractiveness. It can be done. And that's the Pauling scale.
2.5 and 3.9.
Write it down on the board. All right, so
1.4. So it's whole.
no, wait a minute. We got, is it 3.9 minus carbon is sulfur 2.5, right? So that's going to be 0.4, right? Because 2 from 3
I thought it was
0.
3 and
3.9.
2 is 1.
Yeah, well, 3.9 minus 2.5. Does that make sense? 0.4. All right, no,
What? But I was just going to write 0.4.
Okay, so we got 0.4. Does everybody see 0.4? And what is the bond type there? I don't have memorized this. Go back in the book. It says 0.4. So we're going to say polar covalent falls into that polar covalent. Now we have our bond type. So we go over here. We draw the molecule. This is carbon with the 4 fluorines around it. Does everybody see CF4? Raise your hand if you don't see that. Diana. Write this down. This would go in your notes that I gave you when you came in. There's this avid. You want to write that here. This would be very important. So we have our carbon with 4 dots. It desires 8 around it. There are 4 fluorines. The fluorines are in X here in blue. So we now have 8 around the carbon. Now based on this bond type right here, the electron is going to be drawn away from carbon. And it's going to be more negative on the fluorine. Does everybody see how that's the case based on the math that we just did? It says it's going to be polar. The carbon-fluorine bond. So there are 4 carbon-fluorine bonds. Does everybody see that? So if I put this on a graph, right, this is my x-axis, this is my y-axis, and I have a negative here in this quadrant, negative here, and a negative here. If I cut this any way, there's going to be a negative on this side, a negative on this side. If I cut it this way, there's going to be a negative on this side, and a negative on this side. This is the definition of nonpolar. That would be there's no area of opposite charge. See how these charges are the same here? Negative here and negative there. Negative here and negative here. There's no opposite there. The polar, like the magnet, requires there to be an area that's different. This here clearly shows you there's a difference. There's a positive here and a negative here. This looks like the magnet. If it looks like the magnet, it's polar. So overall, nonpolar, negative on outside or no opposite charge at poles. That's nonpolar. The Vesper is tetrahedral. That is, the bond here is around 109. Now we care about this, whether it's polar or nonpolar. Why? This is nonpolar because all the way around it is negative. They're asking about the overall molecule. So you do this to determine what the bond type is. Between this and this, it's polar, so it's going to go in this direction. It's going to go in this direction. That sets up the bond. Their overall molecule is going to be polar because you have an area positive and an area negative. So you do have to look at the individual, and then you have to build the molecule. This is what makes it a little more difficult, which is why it won't be on your test. I'm just explaining it to you because this question came out of the book. So this is going to be overall. See how it says overall polar? This one was polar covalent, right? We did our math, polar covalent. Individually, it was polar covalent. Overall, it is polar. This one was individually nonpolar, and overall, it is nonpolar. The last one is the exception. Because when we did our math here, this is saying it's polar. So you're thinking, okay, that should be producing a polar substance. It does not. Because you have 4 polars around it. And the 4 polars sets up the positive in the center and the negative all the way around it. This is like oil. This is the reason why oil and water don't mix. Oil has a charge all the way around it that's the same. And it repels water. Because water looks like this. Water acts like a magnet. So these two things repel each other. So oil, this is very important because when you go into like organic chemistry and you're making things that you want to be soluble in your body is mostly what? Water. Your body is mostly polar. So you've got to make things that are going to be able to be soluble if you're trying to make a artificial medicine, synthetic medicine. The S there next to magnesium, does it represent liquid or gas? What?
Gas.
Gas? Agree with that, Vance? No, it represents solid. S for solid. So, next to the S, you see the solid there. If you see an L or a G, that's gas and liquid. You see an AQ. What does that mean?
In a water solution.
Yeah, AQ means aqueous. It means the salt, you just put it in water. Can you put salt in water? Yeah, it's called the ocean, right? Carlos, what's it? Potassium what? Right, 2 potassium nitrate. Now, most chemical reactions are like this in that they're controlled. We don't like having too many things in a solution because then it's not controlled. You don't know what you're going to make. So most of our reactions are going to be single replacement, double replacement. Your body does a lot of things in a, I guess you would say, it would seem like a fairly diverse environment. I mean, think about it. There's no test tube or beaker in our body, and it's able to keep all the reactions that are happening separate. That is extremely difficult. We haven't got anywhere near that ability in the labs that we do. the complexity of the reactions that are happening in your body and how they're kept separate. Oftentimes when we even try to do something like that in the lab, they want to blend together. So trying to mimic the body, how it figures out how to keep the reactions and you healthy from not reacting with each other is not easy to do. Not parentheses, but in quotations, what does the S represent?
The electron.
No. Gabe? The state. Now, back to you, Andrew. Is it a gas or a liquid state?
Gas. Liquid.
Liquid?
Yeah.
S stands for liquid.
Solid.
Solid.
Yeah.
Chemical reactions affect every part of your life. They break down your space, producing the energy you need to live. Chemical reactions in the engines of cars and buses provide the energy to power vehicles.